Ooh, it's going to crash. Okay, it's fine. I think it's fine. Okay. It will go from current slide. I may even turn on the projection today. I don't know. I've been thinking. Y'all should be able to get this just from what I say. Okay. And we'll go from current slide if it will go there. There, it did. Now, let me go over these announcements. Okay. Arrange the order slightly. I think I announced to you before about Scholars Bowl. Did I? Okay. Any questions about that? Here it is. They had their first meeting, I think, today. I saw them in there. Were you participating?
Yeah.
Oh, excellent. Wasn't it fun?
Yeah, I like all this stuff.
Yeah. Okay. So if you want more information on Scholars Bowl, see me, see Amanda. Anyone else participating? Oh, okay. Oh, yeah. Okay, I think I saw you in that. It's a lot of fun. And the math team will be just as much fun tomorrow, and that's from 10 till 12 on the Birmingham West Campus in the Science Building, room C103. All right. I told you more about NCAS. It's the NASA Community College Aerospace Scholars Program. This is from everyone that I've talked with. We've had several students participate. They've all said it was great. So check into it. There's lots of websites you can go to, see if it's something that would be of interest to you. I think I told you about the Board of Governors of Federal Reserve System. They have a couple of opportunities. One is the College Fed Challenge. I have information on that, and there's websites you can go to. And the other is Exploring Careers in Economics, and there's some websites you can go to there. And this one I meant to move ahead, and let me mark Cameron here before I forget to. All right. This is something I saw earlier, but I wasn't at a printer when I could print it. It has started already, but you've got some time. Have y'all seen the flyers about it? Darkness into Light. Okay? It's Alabama Holocaust Survivors through Photography and Art. Created by Miss Becky Seidel, photographer, and Mitzi J. Levin, an artist. The Birmingham Holocaust Education Center has graciously loaned the Darkness into Life, Alabama Holocaust Survivors through Photography and Art exhibit, long name, to the Lawson State Community College Library. The sensitive exhibit of photography there's some wording problem here. It says this sensitive exhibit of photography through bold and thought-provoking art. And I guess that's okay that way, but it just seems strange. Offers a special glimpse into the private memories of 20 Holocaust survivors living in Alabama. This collection reveals stories of childhoods past, stolen family and friends, despair and sadness, cruelty beyond belief, and then stories of bravery, the joy of liberation, and their new lives in Alabama. The exhibit will be on display in the Lawson State Community College Library on the Birmingham campus. It started September the 4th, and it goes through September 23rd. So it goes into another week or so. Esther Levy, the daughter of Toby Kamornik Gerson, will speak about her mother's personal experiences as a Holocaust survivor. This event will take place this coming Monday, September the 16th, 2019, 5:30 in the ACAT Technology Theater. That's over on the Birmingham West Campus. It's the next to the newest building on campus now. The new Academic Success Center is the newest, and then come on into the campus from there, and you'll see the ACAT Technology Theater, Center and the theater on the first floor. Light refreshments will be served beginning at 5, and several exhibition pieces will be on display at the event. So please join us at Lost State Community College for that. It's in the evening. Community people are invited. So bring friends, bring family members. It should be a great presentation. Okay? So if you have any questions, that's coming Monday. It's coming Monday. 5, refreshments start at 5. The program starts at 5:30, and it will be enlightening, to say the least. All right. Is anyone else coming since I called roll? Got you, so I think we're okay. All right. One other issue, a little more personal for me. Normally I have office hours on Fridays from 8 to 12, Birmingham West Campus, B122. I've been assigned to go to Shelton State tomorrow. We leave at 7 in the morning, and the meetings go until 2 in the afternoon, and then there's another 2-hour or so drive back, depending on traffic and stuff like that. So I will not be on campus at all tomorrow. Sorry about that. And I hope nobody was planning to come by. If so, get with me today, and we'll see if we can straighten out whatever it is. Okay, and this is Maya, I think, right? Yeah. All right. Anyone else come in since you called roll? Okay. So what are we about today? Well, the first 2 hours, or what's left of it now, will be building the Earth's surface. And this is a fairly long chapter, quite a few issues in it. And then we will have the lab on chapter 18. Now, it's not specifically 18 because we can't do plate tectonics and move them around. That's not quite what we're doing. So from now on, the labs are pretty much going to be different features of the geology part that we're doing now, and a variety of things. I'm thinking today's may be latitude and longitude, which we've talked about in previous chapters. We'll still be talking about in the future. So that's what today's lab is. Wait. No, today's lab, I don't know. We'll see when we get there. I have it run off somewhere in the stack there. It's there. I see it down there somewhere. Okay. But that's going to be the next 2 hours. I don't think it'll take you 2 hours to do. And then we'll have the test on chapter 18. So if you don't have your formula equation sheet, be getting those together. That will be the last 30 minutes or whatever is left. Okay. Any questions? So we'll just go till 3:15 today. So y'all don't let me go too much past that, okay? Y'all are good at that. All right. Any questions before we get going? Okay. Chapter 19 is building the Earth's surface. And if you look here, you'll see some of the effects of plate tectonics right there. So this is all tied in with what we did in previous chapters. Okay? The core concept here, which you'll find in your text on page 481, is the surface of the Earth is involved in plate tectonic processes, that was chapter 18, that result in the ongoing building up of the surface. Okay? The next chapter, chapter 20, will be how the surface is shaped. That's going to be another fairly long chapter, and we may get started on that Tuesday or Thursday of next week. It depends on how this chapter goes. All right. So the surface of the Earth is involved in plate tectonic processes that result in ongoing buildup of the surface. All right. 19.1 is interpreting the Earth's surface. And here is a term for you. It's defined right. It's on page 483. Okay. You have a really pretty picture there at the bottom of 482. Does anyone remember Mount St. Helens? Were you even alive when that happened? No, you weren't. 1982? No, none of you. Yeah, okay. You remember Mount St. Helens. A volcano, a supposedly inactive not extinct, but not one to worry about volcano in Oregon, I believe it was. No, Seattle in Washington, right? No, near Seattle and Portland. So somewhere pretty close in between. Okay? Blew its top. Okay? Been dormant for, as far as we know, centuries. And just all of a sudden erupted. Okay? That's some of the things we'll be talking about today. May 18th, 1980, 8:32 in the morning, became the deadliest and most economically destructive volcanic event in the history of the United States. 57 people were killed, 250 homes, 47 bridges, 15 miles of railways, 185 miles of highways were destroyed. Okay? An inactive, supposedly dead volcano came to life. Now, what happens when volcanoes erupt? Basically, lava comes out. So do you think Mount St. Helens grew? Got taller? You think so? No. It blew the top off the mountain. So it actually got shorter, okay? And what you see there in your text shows what was left. This is 1982. It was still spewing a little bit of steam, letting off some steam. But you see the whole side of the mountain, the near side of the mountain was blown off. The top was blown off. It actually became a shorter volcano. You can't tell the lava flows there, but you can tell there are no trees up the mountain. 2 years later, they still hadn't grown back. And it was pretty rugged soil there too. So that's just one of the things that happened. But here on the next page, we'll see the principle of uniformity. The present is the key to the past. Now, there's a contrast we're going to be making here, and they take a while to get there. Okay? Rocks are changed today by the same process that changed them in the past. Remember at the end of chapter 17, we had the rock cycle. You know, all those ways rocks can become other rocks and then melt back and become new rocks. And, you know, it's all that. The rocks are going through cycles. So they're being changed today by the same processes that changed them in the past. Okay? In fact, all of our surface, all of our plates, everything is undergoing the same changes as before. Now this replaces, here's the contrast, the catastrophic models of previous thinkers. Sure, there have been catastrophic events. There always are. Mount St. Helens was one. If you were one of those 57 people, it was very catastrophic for you. They were killed. If you were working, if you had land in that area, it was catastrophic. I mean, your fields were wiped out. The highways were wiped out. The roads were wiped out. The railroads were wiped out. The bridges, yes. Okay, very good point. I'll get to that. It wasn't all bad because, okay, now what is the state of Washington, particularly for the Pacific Northeast, what are they known for? I was eating one just before lunch. During lunch. Say again?
You said east, you meant west.
Say again?
You said east, but you meant west.
Northwest.
Okay.
Say again? Eve was famous for one of these. Oh, an apple, yeah. They grow great apples out there. Apple orchards wiped out. But, as Ian was suggesting, after that, they had some of the best apple crops they've ever had. Because the volcanic ash is adding lots of nutrients to the soil that had been somewhat depleted by repeated farming. Okay? So, sure, catastrophic events happen, but when they do, typically, well, the earth just goes through this process over and over again. Hurricanes are terrible, aren't they? If you talk to any shrimpers down on the Gulf Coast, they tell you they need a hurricane every few seasons just to wash out the grunge so the shrimp and clam and whatever other seafood that they harvest there, they come in and they grow back within a few years better than before. So catastrophic events do happen, but they're usually followed up, not always, but usually followed up with some things that are not quite so bad. Now, tell that to the people in Puerto Rico. Okay. Maria was catastrophic, and it's been a long, slow process. But when they do get it back, they'll probably have a better infrastructure than they had before. It's going to be built more hurricane-proof for sure, and lots of new things. Now that's man-made. Nature usually takes care of itself too. The people in the Bahamas are probably not too thrilled about the events of the last while, but they will happen. Now sure, catastrophic events contribute nonetheless. There are volcanoes, there are earthquakes, meteorite impacts, there's all sorts of things happening, and they've happened in the past. They're happening now, they were happening in the past. The present is the key to the past. That's the principle of uniformity. It's kind of what goes around comes around in another sense, you know. It's just happening. Now, there are some things, such as the destruction of the dinosaurs. Now, there's lots of theories on this. I still don't think everybody knows what happened. And that was probably some catastrophic event precipitated a lot of that. Okay? So, yeah, there have been things like that happening. But by and large, the same things that are happening now were happening back then. A few times it may have been more major than what it seems like now, but by and large, they've all been happening in the past. And now here's another big word, diastrophism. Okay? Trying to find exactly where this shows up. I'm having a hard time seeing it. It used to be highlighted, but I don't see it now. And by the way, principle of uniformity is also called, if that word wasn't long enough, uniformitarianism. Okay, that's a nice one. And right now I'm not finding diastrophism in your text, but I'm sure it's there somewhere. I'm just not seeing it on these pages. But here's what that means. The process of deformation that changes the Earth's surface. Diastrophism. Now, don't sweat that term too much. We're going to be talking about the features of that. This process of deformation produces the structures such as plateaus, mountains, folds in the crust. Mountains, we're going to learn there's about 3 or 4 different ways mountains are formed. Folds in the crust, and these are related to, especially the mountains, volcanism, the movement of magma, we were just talking about Mount St. Helens, earthquakes, another plate tectonics result, okay? The basic working theory of all this is plate tectonics. That's what we blame for most of this. Now, in the last chapter we talked about the Tibetan plateau. That's been raised up to be what it is by the convergence of the Indo-Australian plate with the Eurasian plate. It's been raised there, as are the Himalayas right next to it. Okay? Don't know that all plateaus are done that way, but there certainly are some. We'll see in one of your labs, I can't remember if today's or a soon-to-come lab, there will be you'll look at a couple of features of the Earth, and we won't study why they existed, but those features come from this deformation that changes the Earth's surface. Okay? Diastrophism, all of it coming from, pretty much from plate tectonics. Now, here are the specifics. These you do need to know about. Okay? Number 1, stress as opposed to strain. Now, If those two sound like they're fairly similar, they are related, but they are different. I think of this way. This is just sort of my weird way of thinking of it. Stress is sort of the verb, the action. Strain is the object of the verb, the result of that action. Now that's my way of looking at it. You may want to do it first. First, stress is the forces, that's the action, tending to compress, pull apart, or deform a rock or a structure of any nature. That's the stress, the force that tends to do that. There are three specific stress forces, and if these sound familiar, they should. The end of the last chapter, we talked about plates, and what were three types of plate activities? Converging plates, diverging plates, and transform, moving past each other. Well, looky here. Compressive stress, that's when things are being pushed together, plates are moving together. Tensional stress, that's when plates are pulling apart, diverging. Shear stress, plates sliding past each other. Same three concepts, just slightly different wording. Okay? Compressive, tensional, and shear. Now, these are plates. It's also rock. It's also macro systems, micro systems. They all go through the same, maybe different degrees of stresses, but the same type thing. We'll look at some of those on smaller scales than plates. We're mentioning plates here. They don't have to be plates. They can be much smaller scale than that. Now the strain, that's the adjustment to the stress. Sort of like the object to the verb. Okay? What comes because of that stress? Three stress sides. Really Trinitarian here, aren't we? Okay. We have elastic strain, plastic strain, and fracture strain. Let's take them one at a time. Elastic. What do you think of when you think of elastic? Second?
Rubber or something.
Okay, you think of rubber, and you usually think of things that stretch, right? That's not really what elastic is referring to, though that is important. What is important is it returns to its original shape. It's not the stretching, it's the returning that makes it elastic, okay? Returns to the original shape. Not that it's stretchable to begin with, it's that it returns to its original shape. Any of you ever hit a baseball or a golf ball, okay? Do you think you deform those balls in when you hit them? Second?
You can dent them.
Say that again?
Dent them. You can like dent them.
Okay. Okay, maybe a little bit. Okay. You really ought to go, I'm sure somewhere on the internet you can find these. Look at a slow motion shot of a golf club hitting a golf ball, a baseball bat hitting a baseball, a tennis racket hitting a tennis ball. You will be amazed. That baseball literally wraps around the bat to a certain extent. Not just a little nick or a dent, it wraps around it. The bat also deforms a little, but the baseball returns to its shape, the bat returns to its shape. That's an elastic collision. Now, a few people have hit a baseball before and the bat's broken. That's a fracture, okay? Strain, okay? But most of the time, it's elastic. You don't notice the bat has been deformed, but it has. You don't notice that the ball was deformed, but it was. Golf balls, I think, are even worse. Those golf balls actually flatten out on the head of that golf club. And the golf club flexes back, they flatten out, but then they spring off and go. Elastic strain. Returning to the original shape. It was deformed. It was really deformed, but it returns. Now I have, any of you play volleyball or ever play volleyball? Okay. Are volleyballs hard or soft? Soft. Softer than baseballs and golf balls. Okay. But are they really that soft? No, they not so much. Okay, nothing like a sponge ball or something like that. Okay, and I remember when I was in college with undergrad and grad school, I usually played intramurals just because I liked to get out and do something, get blood flowing, something. And when I was in my doctoral program at Nebraska, some of us got together and were on a co-ed volleyball team. And we had a lot of fun. We great and stuff, but we had this one really tall gal who had played in high school, and she was a really good spiker. And she had this friend who had, I think, played with her in high school, who was an excellent setter. Okay. And then the rest of us weren't all that great, but we were okay. But then we went to play this one team this one day, evening, or whenever it was. And they had this really tall gal. Boy, was she ever a spiker. And she had this setter who was an excellent setter too. Maybe no better than our setter, but she knew what she was doing. Both of them did. So we knew we were probably going to be in for it. And you know, when you play volleyball, each team rotates sort of in opposite direction. So at some point, you're always opposite everybody else out there. You know, just the way your rotation goes, it happens. So when it was my turn to be against, and boy, that setter could set it up for him, that gal could really spike that ball. So when it came time, and I was across from him, knew it was coming. You know, everybody knew it was coming when you were across from her. And the ball went over there. They got it to the setter. Here it comes. So about the time, I tried to time it best I could to get as high as possible, create as much blockage as possible, because I knew that spike was coming down. And boy, did it come down. Nowhere close to my hands, that ball hit me square in the face. Square in the face. I felt it touch both ears. And then bounced back on my side of the net, unfortunately, undeformed. It was elastic. It returned to its original shape, but all I saw was Wilson, you know, but that was another story. Okay. But anyway, that's elastic strength. The result of a stress can be elastic. But not all stresses produce elastic strain. There's also a kind called plastic strain. And this is actually what you were describing when you mentioned the knit. Okay? The slight deformation. Okay? When you have something molded or bent that does not return to the original shape. Like, now I don't know, y'all are probably too young to remember this. There was a brand of car built in Tennessee called the Saturn. Any of you remember the Saturn? And one of their commercials was, I don't know that this is true or stuff, the kid in the yard throwing the ball somewhere, hit the side of the car and the door, and the father looked up and the door came right back. It was elastic. It returned. As opposed to when a ball would hit and create a dent that stayed there. That was plastic. Molded or bent, not returning to the original shape. That's a plastic strain. That's the result of a stress that didn't return to the original shape. When it bends, when it folds, most benders don't pop back, okay? Not without a lot of work. So those are plastic strains. Now, one of my best friends in high school, we were at a very small high school, 86 in our graduating class, and we were the biggest class ever at that school. And the guy that I was fairly close to, and we roomed together in college when we went to Georgia Tech, his dad was one of the few fairly well-off people in town. And when Paul turned, I think it was 16, may have been 18 or so, he got a new car. Now, maybe that's pretty standard nowadays. It wasn't back then. We didn't get new cars. We didn't get used cars generally, okay? We may have get to drive the family car, you know, but that was about it. Paul got a brand new, not just any old new car, a brand new Chevy Corvette. Woo. Orange. Okay? He treasured that car. And one day, I don't remember who did it first, it seemed like it was his mother, was backing Paul's car out of the way so she could get out of the driveway, and didn't judge it well, sitting real low, wasn't used to it, backed into a tree. Had a fiberglass body. That doesn't elastically strain. It doesn't plastically strain. It fractures. Fiberglass may have a little bit of elasticity, not much, not too much plasticity, but boy, can it fracture. And into the shop it went. Well, a few weeks later, after he came back from the shop, his dad needed to move the car to get it out of the way and didn't see there was a sprinkler head there because it was too low to see. Backed into it, took the hole, fracture strain in the car. Paul, being a little bit melodramatic perhaps, and precocious perhaps, said, nobody else drives my car except Dave. His younger brother, Dave, was such a good driver, he said, Dave can drive it, that's all. Paul took off and went somewhere. I think he was at Governor's Army program or something. He was gone for a while. And he gave Dave instructions. Now, every week or so, I want you to take it out carefully just because it needs to run. Okay, and he was gone for like 6 weeks in the summer. So take it out and make sure everything's operating well. So Dave was sitting at a stop sign on Liberty Street, Main Street of town, near the post office, and a car coming toward him just ran the stoplight from that side and hit a vehicle going down this side, swung it around, crashed it. Dave was just sitting there, not even moving, and the car fell apart all around. Fracture strain. Okay. When he finally got it out, he gave up and said, anyone can drive it once. Okay. He sold the car in a few years. Anyway, but that's fracture. Rocks do the same thing. They can return to original shape. They can deform, bend, or mold, or they can actually fracture. Why go into this? Well, this determines what we're going to have. Is it going to be an earthquake when it finally fractures? The elastic, it could be deforming, and then spring back. That could be an earthquake. Or it could bend and fold and maybe not create much problem at all. These all can happen. Stresses are the forces, compressive, tensional, or shear, strain, that's the result. Elastic, plastic, or fracture. So let's look at stress and deformation. Possible material responses to the stress. Absolutely no change. You know what I'm going to do? I'm going to hit this concrete block. Not as hard as I can, but hit it. Okay? Did I do anything to it? Y'all didn't notice any bending? You did. I didn't hit it hard enough, didn't I? I'm not going to deform the block. Sometimes the possible stress, whatever my mighty blow was there, had absolutely no change on the rock, on the wall. Okay? No change at all. Okay? Now, I can push on this. Well, hey, I moved that one. But guess what? It came back. Okay? It came back to the original shape. That's an elastic change. With recovery, it comes right back to where it was before. Rocks can do the same thing. They have no change at all. They can change but come back, just like we talked about before. Or, when the guys were putting this board in, this is the third one, they dropped it on the corner and bent it. That's a plastic change. Did not quite recover from that, okay? Not at all, okay? And then, if they had dropped it harder, which sometimes I wish they had, actually broken it, then that would have been the fracture, okay? So this is just basically going over the same three strains to a potential stress. Now, possible material responses. What are the rock variables that determine which of these is going to happen? Now let's get away from boards and walls and things like this and think of rocks themselves. Well, number one is the nature of the rock. Okay? Now, in the last lab that y'all did, you recorded some features of rocks. So you were talking about minerals. You could extend that to rocks. What were some of those that might be influenced by the nature of the rock? When you have a strain on it, a stress on it that produces strain. Remember some of the ones you were recording? Color, nah. Street, nah. What were some of the ones that might influence this? Nature of the rock. Say again? Density could easily be one, and that might also be hardness. Remember, Mohs hardness scale. Okay, and remember also you had cleavage and fracture. Okay, the fracture, yeah, the nature of the rock. Do they have these cleavage planes, or do they tend to fracture if they're done? So those are the nature of the rock. The hardness, the chemical composition, all those are features, rock variables, nature of the rock. Now, remember we talked also about some rocks were formed way down deep, some closer to the surface, some on the surface and stuff. What's a variable associated with where they are? Especially if you go way down deep. Say again? Age. Okay, that could be. Okay.
Pressure.
Say again?
Pressure.
Pressure, exactly. The deeper you are, the more pressure it's on. Okay? Nearer the surface, less pressure on top, but maybe still pressure from beneath. So the pressure of the rock, but also the temperature of the rock. Now what happens when a rock is hotter? Is it more tending to break, to bend, or to return to its shape? To bend. The hotter something gets, the more plastic it becomes, the more likely it is to deform. So you see that enters the thing. The rock variables, what's the rock like, what's its nature, its chemical composition, those kind of things, hardness, those kind of, the temperature, where is it in this profile? Is it really hot down there? It may bend. Cold is probably going to fracture or, whatever. Speed of the stress application. Okay? If I were to push on this desk and just keep pushing to slowly increase my push, as opposed to right by karate chop, which I don't do because I don't want me to destroy the desk. Right. Okay? The speed at which that stress occurs, that could have an influence too. If the rock is hit suddenly, I can press on a nail all I want to. I'm probably not going to push it into that piece of wood. But if I take a hammer, and with about the same force, total force, but hit it suddenly, then it will drop it into the thing. So the speed of the stress application. And then what Patrick was talking about, the confining pressure. Is there more pressure underneath or on top or something? That could contribute to whether it bends, breaks, folds, whatever. Okay? And the interplay between all of those produces the observed rock structures. Now, what are some of those rock structures? By the way, 19.2 was stress and strain, the previous slide. Now we're getting into the, this is part of it. This is figure 19.3 in your text on page 484. All right. Now, this represents two different structures. They could be rocks or whatever. Here's A, and here's B. Now, I found find this graph to be a little backwards in my thinking, but I'm sure there's a reason they did it that way. Most of the time, I'm used to putting the independent variable on the horizontal axis, the dependent variable on the vertical axis. This seems backward to me because the strain depends on the stress rather than stress depending on strain. Because you apply the stress, the result is the strain. So it seems like these would be reversed, but then the graphs may not do the right thing. So they reverse these, put the stress vertically, the strain horizontally. So at zero stress, you have zero strain. No forces, anything on the rock, it just sits there, okay? Now, or whatever you're dealing with. You put a little bit of stress, you're going to create some bending, okay? And as long as it's just a little, more than likely, it will come back, okay? That's stress-strain, linear relationship here. Rock A with a little bit of stress deforms a little bit. Rock B deforms a little bit more. Same stress, but greater strain. A little more strain. But it comes back. As long as it comes back, that's your elastic strain. Straight line, linear result is elastic. Now, rock A here, or object A, at some point, you keep adding stress, keep adding stress, keep adding stress, and now one of two things is going to happen. It reaches a point where it can't return, okay? And it either permanently deforms, that's plastic deformation, or it ruptures. Rock B, it ruptures. It doesn't have, okay, both of these have reached the elastic limit here and here, but this one turned into plastic deformation. This one actually ruptured there. You continue adding, at some point it's still going to rupture. Okay? So this is kind of like, have you ever taken a spring out of a pen? You've been sitting there playing with it. You probably shouldn't have been sitting there playing with it, but you were, yeah. And stuff, and as long as you don't stretch it too far, it comes back. But if you get sort of carried away and all of a sudden stretch it too far and it doesn't spring back, now you're in plastic deformation. The spring just is over, like that. Now, if you had really pulled on it too hard, you may actually break it. And that's possible. I can't recall doing that before, but it is possible. Okay? That's a rupture. Other things, I think, specifically things like glass, they don't have very much plastic deformation unless you heat them up. And we talked about that before, but at normal temperatures or at very cold temperatures, you add too much, they're going to rupture. No plastic deformation. But again, some of these variables could enter that picture. Does that make sense? Okay. Now, this is still 19.2, Earth's changing features, it's called here. The first of these is folding. Now, probably all kinds of rocks can fold, but it's hard to tell when they fold it, okay? Now, this isn't like gambling. This is not that. This is the ones that we can tell the best with are sedimentary rocks. Sedimentary rocks usually settle out horizontal sheets. Sheet after sheet after sheet, okay? Layer after layer after layer after layer. That's what makes sedimentary rocks, right? Now, the original sediments are flat sediment. Flat sediment deposits one over another. This one may be reddish in color, and then later plankton comes in, and then something else, and you get these layers, and you can see those in the sedimentary rocks. Other times, hard rock will be here, and in between softer rocks, and then hard rock, and then they eat away, erode away. The softer stuff comes out first, and you can see the layers. Okay, that's sedimentary rocks. That's how they form. Usually horizontal layers. Now, when you later look at some of these things, you can see bends in that layered bedrock. In fact, remember that one rock we saw twice in the last chapter? The last chapter or chapter before? No, last chapter. And it had all this. I mean, you could see those sedimentary layers were just all bent, twisted, and all sorts of things. And here's, oh goodness gracious, Maurice, right? Okay. It was one of those nice rocks, okay, remember? Had all kinds of bending in it. So those are folds. When the bends in the layer of bedrock, you can tell it's been bent. These result from stress producing plastic strain. If you have bends, that's plastic strain. It didn't pop back and go horizontal again. That was plastic strain. The odds are, when that originally happened, way, way deep and hot in the earth. Okay? That's how you get plastic strain. Widespread horizontal stress can produce domes and basins. Now, I don't know for sure that this is one, but have any of you ever seen Stone Mountain, Georgia? I'm not talking about the carvings on it and stuff, just the big mountain there, okay? It's not really a mountain, but it's one huge chunk of granite sitting on fairly level land there, okay? I don't know for certain, but I wouldn't be at all surprised if this wasn't the result of widespread horizontal stress from below that forced that thing up into the structure that it is now. It's pretty much flat all around with this huge hunk of granite sitting there, Stone Mountain, okay? But there are other places where you can see these big dips there, almost lakes forming, or as in some of the areas near where I grew up in Georgia, they were called Grady ponds. Basically, what happened is there was a probably Selma chalk or something like that underneath, and as it deteriorated, acid rain and that kind of stuff, then the chalk deteriorated, became carbon dioxide and stuff, and the soil just sunk around. Maybe a sinkhole is like that. Sometimes that's a physical thing, but that's what happens sometimes. So that would be your, where is it here? Produce domes and basins, the lowering part. That would be, say, a Grady pond or something like that. Grady, Grady. It's not in your book. That's just what I remember from soil science. By the way, my background, I grew up on a farm, okay? My undergraduate degree was in physics, and somebody along the way said, well, you could always do soil physics. I'd never heard of that, so I didn't really want anything to do with it. Then, as I got older, I thought, I'd like to apply this physics I've learned to something like agriculture, which I know about, and feed the world type kind of, young, what is the word for it? Optimistic, that kind of stuff. So I got into that, and so this chapter, and especially the next chapter, are my favorite chapters, okay, because they're dealing with this kind of stuff. So a fold, if it's an anticline, now here's how I remember it, arch-shaped, okay, anticline, A, arch-shaped structure. This is an anticline. What's happened here, the pressure from underneath, probably way, way underneath, where it's really hot, it's bent or folded this, and you have this arch-shaped structure. Here's the younger strata on top, then this and this and this, and here's the oldest down here, and that's probably where the uneven pressure that Patrick was talking about came from, okay, making the anticline. Whereas, on the other hand, if it had formed the other way, like those Grady ponds, as you're losing the stuff underneath it, that would have been a syncline, and that's called a trough-shaped structure. So let's see, here would be a syncline, okay? And the younger strata is down here. Older strata up here is old, right next to younger here at the same level, but this is sunk because somewhere under here something gave way, the pressure was less, and it did. But it had to have happened deep enough at hot enough temperatures it didn't fracture, it bent, permanently bent. So this is a fold. Syncline if it's up, anticline if it's up, syncline if it's trough shaped. Any questions on that? Okay. So, continuing with folds. The folds are bends in the layered bedrock. We count layered sedimentary soil so we can see them better. It's hard to tell in an igneous rock whether it's been bent or not because there's no layers that you can measure by. So the sedimentary rock. The bends in the layered bedrock result in stress produced by plastic strain. No, stress producing plastic strain. Bending strain. Widespread horizontal stress can build onto, that's the same thing we just saw, but it's on a different thing. Here we go. Now, anyone recognize what this could be? I don't know for absolute certain of what it is. It could easily be the Grand Canyon. Would you say there's been a lot of stresses there? No, there's been a lot of erosion there, but look at that. All the layers are horizontal still. You haven't had any bending or folding to speak of. Okay? This would be the previous slide when they were talking about sedimentary falling down, coming down in horizontal layers. This, however, there's been some forces here. This would be a what? What would that be? Trough-like? Syncline, where this would be an anticline, exactly. Okay. You see, somewhere under here there must have been forces, and it must have been very deep when it happened, very hot when it happened, because you made bends in the bedrock, not breaks. Okay? Syncline here, anticline there. Looks like another syncline forming there, maybe another anticline here. Differences in pressure underneath that created this bending or folding of the surface. And you can sometimes see that. I'm trying to think if I've seen it anywhere on road cuts. Can't recall around here anyway. Talk about a pretty big one. This had to have happened way deep. This would have been a syncline, anticline here. Boy, look at that. You can see the scale of this. That's pretty major. This had to have been sedimentary rock because you can see the layers. They were originally horizontal. Something has happened. Pressure from underneath raised this. Lack of pressure here caused this to sink. Okay? Now, you might see some cracking and stuff. That's usually probably erosion from this happening. It didn't look like that was originally part of it. We'll talk about that in the next chapter. But there's pretty major folding going on there. Okay? Big scale. Big scale. All right. Now here was originally a dome. You don't see much of a dome anymore, but you see the remnants of it. Okay? And they do give the name of this one, I think. Let me see if I can find it. Yeah, the first one that we saw was the Grand Canyon. Let's go back and that top one there is the Grand Canyon. The second is just a road cut. Okay? Ooh, I'm going the wrong way. Okay. This isn't exactly the same picture, but what they call it in our book is tortured rocks from originally horizontal layer that were folded by intense pressures, high temperatures over long periods of time when deep underground, but they don't tell where that was. maybe the same area, but just a different picture of it. Okay. Now, this one of the texts has shown that before. I don't think ours shows it. Wish it did. Okay. But this, I believe, is around Sundance Mountain. And those of y'all probably are too young to remember with Cassidy. But Sundance is actually an area. And this was a dome that existed and then eroded away. And the oldest rock are in the middle here, and the newer rock around the outside. And this was a dome that came up. And here's Tamaya, right? Yeah. All right. Slowly we're getting here to a good number in class. Okay. And this is a diagram of what you see here, a pictorial diagram. The youngest formations out here, the older formations are in the center that have been pushed up. But these happened way, way, way earlier, way underground, as they came, for whatever reason, toward the surface. Then you had the cracking. We'll talk about this in the next chapter. Breaking away and erosion happens, so you don't have a mountain here anymore like Stone Mountain. You have the residual part of a dome. I believe that was at Sundance Mountain. Now, before we go okay. Let's move into what we call faulting then. Okay. This begins on page 485, and I mentioned that for a purpose, because the slides don't make as big a deal about this as they did in the test bank. Hint, hint. Sometimes rock layers do not always respond to stress by folding. In fact, you've just about always got to have a significant amount of heat and uneven pressures and things like that. Okay? Now, rocks near the surface are cooler, under less pressure, and they can be more brittle. And when they're more brittle, they tend not to bend, but to break. Okay? And that's what we're talking about with faulting. A sudden stress on these rocks may reach a rupture point, which we saw earlier, resulting in cracking and breaking of a rock structure. Here's the sentence I'm wanting you to see. If there is breaking of the rock without a relative displacement on either side of the break, that crack is called a joint. Okay? That crack is called a joint. And here's Edward. Okay. However, if there is movement on one or the other side, then that's called a fault. So there's this little bit of a difference between a fault and a joint. A joint is a crack, but no relative motion on either side. A fault, on the other hand, will have relative motion. Now, in your text, and they don't show it here in the slide set, there are two really incredible figures. One is columnar jointing, forming right angles to the surface as the basalt cools. Okay? And this is worth showing if people at home can't see it, but get your books and you can see that, page 486. Here are basaltic jointing here. No relative motion between them, but you do see the cracks forming. Now, these are places where they've fallen down, and look how distinct those are. It almost looks like that's cut stone. The odds are it's not. It's just jointed that way. Now, this is one we're going to be talking about. No, it's not quite the same one. We will have in The next slab, or the one after that, not quite this one we're talking about. It's called Devil's Tower, not Devil's Post Pile. They're similar, but different locations. This is San Joaquin River, California. These are basalts. Oh, and here's one. I'm sorry. This is Devil's Post Pile. That's here. And this one is Devil's Tower in Wyoming. This one we'll be talking about in a subsequent lab. Not this lab, the next lab, but one coming up soon. So remember this picture when you get there. But these are joints here where there's no movement between the cracks. Where you do have movement, that's called a fault. Okay, both of them are breaks, but one was no relative movement and one with. All right, so let's move into the faults where you do have movement. Produced by relative movement on opposite sides of a crack. If there's no relative movement, what's it called? A joint. If there is relative movement on either sides of a crack, it's a fault. Now, usually the faults are at angles. You almost never have one that's just straight. I guess you could, but most of the time they're at angles. Those joints, they can sometimes be almost vertical. But most of the time these are at some sort of an angle. Okay? Now on the angle, there's a bottom side and an upper side. The lower side is called the foot wall. The mass of rock that's on the lower side of the fault is a crack, okay? And the foot wall is the mass that's below the fault. The hanging wall is the mass of rock that's on the top side of the crack, above the fault. The fault plane is that plane that cuts through. It's a two-dimensional thing, not just your pictures of it are all one-dimensional, but it's the surface between the foot wall and the hanging wall. So here's somewhat of a picture of that. Okay? What is this part? The right-hand side. That's the foot wall. Even though it's up here, it's been elevated, it's the foot wall because it's on the lower side of the plane. This is the fault plane. This would then be the hanging wall, even though it's hanging down, it's going downhill. How about this? Which of these is which? This is the foot wall. Here's the hanging wall. Again, the hanging wall went down. You can tell by the streak here. This was at one time lined up with this. This was lined up with that. You can't see the other part here, but you can tell by the coloring, the sedimentary rock, the different layers. This one fractured. This was a fault, not a fold. Fold is continuous. Fault is not. Okay. Pretty clean break too. That's an actual picture, not just a drawing. Any questions on that? Make sense? Now, there's several classes of faults. Okay. Not my fault, okay. First is the normal fault. The normal fault, the hanging wall has moved down relative to the foot wall. That's called the normal fault. Now, at some point they'll get around to telling you some differences here. I wish they had done it now, but we'll get to it. Here are some related features. Don't worry about these terminologies, but if you ever need it or run into it, you can say you've seen it somewhere before. When you have a block that's surrounded by normal faults, so the normal faults have dropped down, and here's Tegan. Okay? The normal faults have slid down, normal faults, and the block that's surrounded by the normal fault, well, I'm sorry, I said it backwards. The block surrounded by the normal faults, the block slides down. So here's your normal faults, okay? Fault plane here and here. The hanging wall has fallen down. That's what makes a normal fault. When that's happened, it's called a graben. It's called a horst when the normal fault, the block surrounded the normal fault is uplifted. Now what's really happened, it wasn't uplifted. The rocks on either side fell down, leaving a mound here. That's a horse. If it's a graben in the middle, and here's the pictures of them, or at least drawings of them, this would be your normal fault. The hanging wall has slid down the footwall. Normal fault. Now they finally got around to showing the stress here. These are all strains. The stress that caused this had to have been what kind? Remember the three types of stresses? Compressional, tensional, shear. Which was these? Tensional. Tensional stress because the hanging wall fell down the footwall. Slid down the footwall. It had to have been a tensional stress. Okay? Now, it seems like to me that would have been not the normal, but that's what they call the normal. Now, when you've had two of those, again tensional, and the hanging wall slid down between two normal faults that go at this angle, this is your graben, where the block surrounding the normal fault drops down. And truly it did. Okay? Here is the one that I sort of disagree with the way they say it. It's uplifted, but really it probably wasn't. If this was a tensional fault, which it was, normal fault, tensional stress, then these have dropped down. This just stayed in place. It wasn't really uplifted, but it appears to have uplifted. That's called the horse. And again, don't worry about these. This isn't a memorization thing. So just so you'll know in the future. Now, I don't know. I can't keep them straight because I never use these words except when I'm teaching right here. You might think of this as a horse. You can say, I don't know. Horse, graben, I don't know. I can't even think what you could do to associate that. Okay. Now, there's other kinds of faults. A reverse fault would be then what? When the hanging wall was forced up the footwall. Now, what must have caused that? Compressional stress is perfect. You had to have stresses this way, forcing the hanging wall up the footwall. That would result in a compressional stress. So that's one, a reverse fault. Hanging wall moved upward relative to the footwall. That's the result of horizontal compressive stresses. Now this next kind is just sort of a distinguishing by degree. This is a normal, you guys have an ordinary reverse fault. Okay? But when the angle of the fault is very, very gradual, but it's still a reverse fault, that's called a thrust fault. Now, I don't know where they came up with that word. It seems like thrust would be more abrupt, and this doesn't look abrupt at all. Here it's a reverse fault, but with a low angle fault plane. And most of the time with a low angle fault plane, you're hardly going to be able to distinguish the fault line on the surface. Okay? Because it would have, that's a very thin layer and it probably erodes pretty quickly. But if you study the side cut, you'll see there is a fault there, and that's a reverse fault because the hanging wall has slid up. Had to be compressional forces, but it's a very low angle, so that's a thrust fault. Now, these faults, all these faults, produce information about the stresses producing the formation, which we've just been talking about, but now they finally get around to mentioning it on the slide. Okay. How are we doing time-wise? Okay, good. Now, they do have some examples here in the book, and these are worth a read, but don't sweat them too much, okay? There are some other figures in the text, and before we get to earthquake, maybe I should go back a slide. Yeah. Give me some room to show these. This would be what kind of fault? This one right here. Which is the footwall, right or left? Can't hold it forever. Right, and the hanging wall to the left, and which way, who seems to be on top? Hanging wall, so what kind of fault is this? Reverse fault, and what kind of stresses cause that? Compressive. Okay. Now here's one, I don't know how they classify this one, because that's almost a vertical fault. Okay? At least down here, it appears to be vertical. If you read into it a little bit of this action, yeah, which is the footwall, left or right? It looks like left. And the hanging wall then to the right, and which kind of fault would this be? Say again? Which kind of fault would that be? Only 3 to choose from. Pick one. My arm's getting tired. Say something. Say again. Did someone say normal? Please say yes. Normal. All right. Yeah, that would be a normal fault. Oh, bad. Because it seems like the hanging wall has slid down the footwall. If indeed that curve there is part of it. Now, if that's part of it, it's hard to tell. And that would be what kind of stress? Tensional stress, exactly. Okay. Now we move into earthquakes. We've been talking around earthquakes, about earthquakes. Let's have one on earthquakes. What is an earthquake? It's anything really that causes the earth to move, to shake, to quake, okay, to vibrate, to upheave, something like that. An earthquake is not, this is Hollywood, this is not true, it opens up and people fall in. That is not an earthquake. I don't know what that is. That's a figment of somebody's imagination. That doesn't happen, okay? The quaking, shaking, vibrating, or upheaval of the ground. That's what an earthquake is. Anything that makes the earth move like that. Usually it's the result from the sudden release of energy from stress on rocks. Now, what could be those sudden releases? Let's say that a rock was under a lot of forces, but then suddenly rebounded. Maybe elastic. That could cause an earthquake. Or it was under force, stress, and then it fractured. That could cause the earthquake. So the two opposite ends of things, elastic or fracture. Fracture is more likely to be the case. It just depends on where it is. So it's a result from the sudden release of energy from those stresses on rocks. My gut feeling is it happens more when they fracture. The vibrations are your seismic waves, and we talked about those last chapter. And review with me, if you will, what the three types of seismic waves are. P waves, which is primary waves, which could also be called a pressure wave or compression wave. Okay? The second being the secondary wave, also called a S wave, yeah. What's another word? It's an S word, in fact. Shear wave. Okay? And the third being the up and down, that's the surface wave. Once the vibration reaches the surface of the earth, it causes the things that look like water waves, but it's on the ground. Okay? Or if it's in water, it would be water waves. Also called a tsunami. Okay? So, those were the seismic waves. Which of those are the fastest? Primary waves, okay? And that's why we call them primary. They get to the station first, because they're faster. And which are the slowest? Surface waves. Secondary waves are in the middle. Okay, most earthquakes occur along the fault planes. When one side, there's been stresses, whether tensional or compressive, tensional or compressive, and something is suddenly given, rock split, the fault was formed, whatever, along those fault planes when one side is displaced with respect to the other. When the hanging wall went down the footwall or was forced up the footwall, whichever, with a sudden movement like that, that's when it's happening. Those don't have to be on the surface where you can see them. The odds are they're going to be pretty deep. Okay? So what are the causes? Anytime you see the word theory, that means we don't quite know, but this is our best guess. Okay? The one is the elastic rebound theory, and that's what I was telling you about. There was stress, and then suddenly it popped back to its original shape. That's the elastic rebound. Two plates pressed tightly together. The friction restricts the motion. The stress is built up. They press tighter and tighter together until either friction or a rock rupture. That's not a elastic rebound. If it ruptures, strength is overcome and it gives up. Okay? That could be, it sounds like to me that's the compressional stress causing that one. Could be the other, but mostly compressional. So that seems like that would be the normal, but that's called reverse. Never mind. All right. The stress rock snaps suddenly into a new position. If it didn't fracture and just snaps into a new position, that would be elastic rebound. If it did rupture, then that would be fracture. That would be elastic rebound. But they would both cause the same result. So that's one theory, elastic rebound theory, which could result in elastic rebound or fracture. Okay. Anyone recognize this? This is the famous San Andreas Fault, going kind of up and down the west coast of the U.S. Okay? I wonder sometimes if San Francisco Bay wasn't formed because of a pretty big plate disturbance there at some time. Can't say that for sure. It follows the coast going north. Actually, it's off the coast up here. Now, I don't know this for a fact, but here's my guess. Remember the little one diffuser plate? I think that's the beginning of it right there. Can't say for sure, but I bet you that's part of it. Okay? And then it goes inland as you go south, and the fault is here. It goes right through San Francisco. Los Angeles is on the downside of the fault. But if you notice here, this is going down into Mexico. Okay? And it's going fairly deeply into Mexico, too. And I can't help but wonder, they don't show it far enough from us now, but if I'm able to guess where that is, it shows a fair amount. Most of California's southern border with Mexico here, Tijuana somewhere over here. Most of the southern border is on that side of the fault, and that would be here. New Mexico doesn't pick up until somewhere here, and it looks like the way that's heading, that's going right down into the Gulf of California. This is called the Baja Peninsula here. It's almost cut off from the rest of Mexico by that Gulf of California. And it looks like to me this is an extension of that. That maybe at some time that was a pretty major fault happened there, and it actually split and the water came up. I don't know. They don't show enough for me to confirm that, but it sure looks like it to me. Not very important, but it's there. So here is one of the major fault lines in the U.S. One of the reasons it's major, it has so much seismic activity. on earthquakes. If you live along that, you're experiencing earthquakes frequently. Not major earthquakes, little tremors, shaking. They put the lips on their china cabinets a little taller there, just to keep the plates from falling out, because they experience fairly frequent little tremors. It's not a good sign when they go a few years or decades with no major tremor. Hey, maybe they're over. No, they're not. Okay, there's still those same stresses. What is happening is hit something, and now this pressure is building and building and building. So when it finally does, it's going to be a major. So you don't want that to happen. You'd rather have the little tremors periodically rather than the one major one very infrequently. All right. Now, is that the only major fault line in the U.S.? As I say, no, it's not. As I say, nothing replaces reading the chapter. The PowerPoints don't cover everything, and neither this. If you happen to read here, and this is one of the most unusual ones, one of the largest earthquakes, this is on page 488, on record in the U.S. occurred not in California, but in a region of New Madrid, I think is how they pronounce that. If they were Spanish, they'd say Madrid, but I'm pretty sure they call it New Madrid, Missouri, in 1811. That quake toppled chimneys 400 miles away in Ohio. 400 miles away, chimneys were falling down. It was felt from the Rocky Mountains to the Atlantic coast, from Canada to the Gulf of Mexico. It was pretty major.
What year was it?
1811. Okay, just a little before my time. Okay, and actually, the year before the War of 1812, right? Fire going around the bridge. Never mind. Okay. If I'm not mistaken, and I may be, but if I'm not mistaken, that was so major that the Mississippi River flowed north for a few hours or days and then started flowing south again. It was major, major. That's hard to explain because there's no plate tectonics. I mean, there's no plate boundaries there at all. It's just a weakness within the North American plate. It's the best I could describe it. Just like the Hawaiian Islands are right out in the middle of the Pacific plate, what caused them? There's just a weakness in the Pacific plate, and volcanic islands came up. Okay. Now, this is one of the most incredible pictures to me, being a former farm boy. Now, this illustration here is okay. I don't find it very realistic. But yeah, you have, and by the way, what kind of boundary is between the North American plate and the Pacific plate, or Juan de Fuca plate there? What kind of boundary is that? Is that compressional, tensional, or it's shear? It's a shear boundary, okay? And the shear forces. And here's what gives it away. There's forces on one side going one way, one the other. Never do you see a road bend like this and the fifth bend like this. This is an artist's interpretation. And never do you see that big a shift, that half of the lane, in fact, the full width of the lane. No. Okay? This is more realistic. This is a real picture. This is not somebody's imagination. There's a field out there in California. My guess, I don't know for sure, my guess is down in somewhere in the Imperial Valley or somewhere down here where the fault line is well inland. Okay? This is my guess. They didn't say. I don't think they said. Well, yes, they did. El Centro, California, which I have no clue of where that is. Okay? Anyone know where El Centro, California is? I've never heard of it before this right here. But this is a lettuce field, not that I could tell there was lettuce there, But this was probably, let's see if they say what year it was, 1979. Does anyone remember when the earthquake in San Francisco was? That was the World Series earthquake, the Bay Bridge. Was it 80s? Okay. It could have been. Yeah, it had to have been. Much later. So this was the earlier one. Okay, so this would be 79, way earlier. Okay. Because, yeah, I was working for Southern Research when the Bay Bridge quake happened, and that was around 80. I was married in 86, so that would have been sometime in the next 87, 88, 80. It would have been maybe even late 80s, early 90s. So this was an earlier quake. But look at that. You can tell this earth moved here, that moved here. Okay. Nothing like a lane of traffic, just a little bit of a road here. I would have hated to have to file that few after this. You know, we're going to have some cultivated lakes like there. It's farm code. Okay, but you can see there is shifting. Shear stress. Okay. One plate moving one way, one the other. Incredible photograph. All right. Page 489 is also where we run into locating and measuring quakes. Okay. Keeping up with time here. Now, couple of terms here. You probably all heard people talk about the epicenter of the quake. Okay? That's not where the quake occurred. That's above where the quake occurred. The focus is where the quake occurred. That's the actual origin of the seismic waves. That's where the fault happened, the break happened. It's down here somewhere. What the epicenter is go directly above that to the surface of the soil, of the earth. Where that was, directly over that, that's called the epicenter. And then you move out from there. Okay? And you see, if it was a fault, and which kind of fault would this be? Which is the footwall, left or right? Left. So the hanging wall would be to the right. And what's happened to the hanging wall? Fell down the footwall. So what kind of fault is that?
Okay, wait. The footwall's on the left?
No, footwall's here. Yeah, look on the left, yeah. Yeah. That is only three kinds. Normal, that's a normal fault. Okay? Now, because the focus was somewhere way down here, the epicenter isn't on the fault line. It's down here. It's on the fault line down here, but the epicenter is not on the fault line here. It's on the flat part here. And the deeper that was, then it may be way from where you would think the fault line was. It's above the fault line, but depending on the depth of that. So the epicenter is the location on the Earth's surface directly above the focus. The focus is where the actual origin of the seismic waves. Whatever gave. Whatever broke. There at the focus. Go directly above that on the surface of the Earth, and you're at the epicenter. Now, what is a seismograph? Graph means to draw. Seismic meaning seismologic. So a seismograph is something like this. An instrument used to detect and measure the earthquakes. Okay? Now, it's fastened solidly to the bedrock of the earth. I mean, it is part of the bedrock of the earth. So when that shifts, and it has these this freely moving pinhead here with a heavy weight on it, so it doesn't move just randomly. It's got to do. And then this is a wire here that allows it horizontal motion. When there is ground movement, then it's recorded here. There's always little bits of motion, but then when there's an earthquake, you see major deviation from that background noise. That indicates earthquake. Now, three kinds of waves. What are they? P waves, S waves, and surface waves. Okay? The P waves are longitudinal, meaning compression waves. Where do they travel? Through rock or liquid as well. They can go through molten rock as well as solid rock. The S waves, transverse waves, shear waves, where can they travel? Only through solids. They cannot travel through liquids at all. And that's how we distinguish, and they come up with the idea of the liquid core. Lexi is here. So right now we're missing Brianna, Derek, Chris and Latricia, and Michael Pruitt. Y'all haven't seen him, but he's been in touch with me. Okay, and then the third type is the surface waves. These are up and down waves that happen when the seismic waves reach the surface of the earth, and then they sort of spread out this way. These are the slowest, these are the fastest, these are in between. So, the seismograph will detect the P waves first. Why? They're the fastest. They get there first. They all happen at the same time, but the pressure waves move fastest as the longitudinal waves. They will get here first. Now, they're not always all that distinct. Sometimes the secondary waves make a bigger mark here than the pressure waves. Certainly, if the P waves have died down, then this goes back. But the biggest are these surface waves. When they get there, I mean, they've reached the surface of the earth is moving then, so it really does some jiggling then. Okay? Now, as we said before, today and earlier, the P waves travel faster than the S waves. So they will arrive at the seismographs all over the world before the S waves get there. Now, how much sooner they arrive before the S wave depends on how far the station is from the actual quake. The closer it is, they're going to be there really quick. But the further away it is, there'll be a longer delay. So the difference in the arrival times correlates to the distance from the earthquake. That's the key here. Because let's say we have a station here. Okay? We have a station over here, and we have a station down here. Depending on how long the arrival time was between those two the two things, the P waves and the S waves, they can determine how far it is. And from this point, if you draw a circle that distance around, and from this point you draw a circle that distance around, and from this point you draw a circle there, where those three circles intersect, that is the location of the epicenter on the surface of the earth. And somewhere below that is the focus. What's that? You have to have three stations reported before you can determine. Okay, we'll see that in just a second. That's called triangulation. You have to have three to pinpoint the epicenter and then to determine the focus. Here's an example of that. So here first is the distance. When you're really close to the quake, you get the P waves, and then you get the S waves, and they're really close together in time. This is time this way, this is distance this way. Okay? Again, this is kind of a backwards graph in my mind, but usually time is the independent variable. Distance depends on time. But then when you're far away, the difference is pretty major, and you can estimate from that distance how far away you are from the quake. So here is station X. It's a big difference between here. Somewhere way out here somewhere, you know you're that far away. Station Y was somewhere much closer, and you know you're that far away. Well, the quake could have been here or here. You don't know which. Had to be one of those two. But when you get your third station, that one's down here somewhere, and that one intersects here and there, or there, but the earthquake had to be here because it's where all three triangulate Now, quite often you're going to have more than 3, 4, 5, 6 come in. And then you just are able to better identify that point or identify which one's sort of off. You know, if most of them come in right at a point and another one's sort of off, there's something wrong with that last signal, that signal. Okay? But most of the time they will triangulate very nicely like that. At least close enough. Close only counts in horseshoes, hand grenades, and earthquakes. No. Made that up. Okay. Now, that's the figure you see on page 490. Now, what I wish they had, the new edition of the book has it, I don't have it in the slide set, is this. Let's see if I can get some room to, yeah. I wish they'd have shown this, because this is actually a seismograph. Now, they added the color, okay? This, I think, is actually a seismograph reading. When you're really close, the P waves are the red wave here. You can hardly tell it. The S waves are the blue waves. You can tell that because they're jiggly. And then the surface waves are here. And the P waves create a distinct disturbance, way more than the background noise was. But then they sort of die out. And then you get the S waves, which are actually come in a little stronger. It looks like most of the time than the P waves. Not much, but a little bit. And then they sort of die out. And then you get the surface waves, okay? And those are pretty major here. Surface waves are coming from the epicenter around the surface of the earth. So they're really slow getting there. See, they got a long way to travel this way, but the P waves and the S waves travel pretty much like that. So I like this picture that shows the actual relative sizes of the waves. We use these two, P and S. The surface waves, there could be all kinds of junk that messes with that. But the P and S waves usually travel just about similar paths. So you can, that's the one they use to distinguish the time and therefore the distance. Now, there's other ways to classify earthquakes, okay? Aren't we awfully close? I don't know if we're going to have time to do this slide, so maybe we should pick up here next time. And the main reason I say that is I've got to dig through my stack and find the labs because, like I said, things got a little crazy today with misplacing and misclassifying some things. So let me see. I hope this is in the right order here. And this is all old stuff. And while I'm on this subject, since I'm still recording, I still have 1, 2, 3 people who pretty regularly attend have not turned in the first lab. I'm having to carry all these things around, folks, more than like holding the book up on the board while I'm waiting for someone to come up with an answer. I don't like carrying all this stuff. I'm too lazy for this. Please get the labs in, okay? The first test, I'm missing 1, 2, 3 that regularly attend there too. And they're not necessarily the same people either. Lab 2, missing 1, 2, 3, and again, not necessarily the same people, not turned in lab 2, test 2, 1, 2, 3 that regularly attend, not all the same, okay? Lab 3, hopefully y'all are working on, right? Your moon lab, okay? Keep working on it, get that in as soon as you can. I told somebody last time, I forgot to tell the class, last Thursday evening after class, I got home and we packed up and decided to go on and head out to Georgia because we had some business to take care of there. I grew up in Georgia and we have the farms that both my parents have died and the farm has been split up, and we got rid of the cattle and we're planting pine trees. So I had to meet with the forester on Friday. So we tried to get over there on Friday so we could take care of things. And we were driving home, and I could look out the window there, and there was a perfect half moon. I mean, it looks picture perfect, cut directly into exactly a half moon. And we arrived home about midnight. So about 15 minutes before we were home, I looked, and that half moon was sitting right on the horizon. Guess when it was setting? Midnight. Remember that, lab? That's what we said too, wasn't it? So we verified that. Now, which half moon it was the first quarter moon, okay? Because now we're into what kind of moon is out there now? Second? It's very close to a full moon. The last couple of nights, you could tell it was gibbous waxing, okay? So it was, that was the first quarter moon then. Okay. So those are in the right order. These are the ones she completely got totally out of order. And these are the ones I had copied. So I found the lab.
So we didn't get break.
Second?
We have time to take a break now then?
Yeah, we're going to have a break right now. I'm going to give you the lab first so you can go. Now, let me explain something about this lab. This lab is going to be one we actually will do in the laboratory, not in this room. Okay? I don't know which lab we'll use. I've got to go find out which room is available now, which lab is available. Hopefully 259. But if we can't use that one, we'll come up to either 253 or 252, one of those two. But I've got to carry some equipment up there then. And it's only a 10-point lab. So the other 15 points are going to come from answering questions at the end of the chapter. So we'll talk about that later. So it's a very short lab. 10 questions is all we're going to do today. But you can work on your other. You need a copy too?
So are we about to move, you said?
What's that?
So you said we're moving out of here?
We will be moving. I don't know where yet. Okay? I've got to go find out what room is available. I hope it's 259. If I give you too many, return any unused students. Okay, so why don't you take a break and come back here. If we've already gone, I'll put on the board what room we're in. 259, down the hall that way, down the half flight of stairs. 252 and 253 are down this hallway, no stairs, first two doors, one to the right, one to the left. 253 is over here, 252 is on that side. I'll try to find out. I think both of those are open. I just hope that 259 is open. Okay. Okay. Still got to keep all these things in misorder.
So the size of the waves has nothing to do with the distribution.
Oh, wait. One more thing. Does anyone need a book? I thought I had one, and finally I found it. Does anyone need a book? Okay. Someone donated that. Couldn't find it earlier. Yeah, what's your question?
The size of the we're going to be on break, but we don't know where we're going.
Right.
So we
Come back here, and
come back here.
I'll either be in here or I'll write it on the board.
Yeah, right on the board. That's perfect.
Right.
The size of the waves.
Right.
The wave has nothing to do with the destruction, right? Because the destruction is right around the epicenter, right?
Yeah.
The waves are just what tells us how thick it was. I
Okay.
mean, that's what registers it, right? That's how they measure it. It was a 7 or an
Okay.
8 or whatever.
That's coming up. Okay. There were several ways that we've measured in the past. Some of them based on destruction.
Yeah.
And that was in the past. Now they use it based on the amount of movement that actually occurred. So if you had one out in the middle of nowhere,
There would be no destruction.
hardly any destruction, but could have been some major movement.
Yeah.
So yeah, we'll talk. Remember, I talked about the one in Chile that had damage, but not too much. Or the one in Haiti was major damage. The one in Chile was stronger earthquake, but their buildings were
They had better reef.
had better. Yeah,
Haiti has nothing.
yeah, right,
They live in like stick houses.
right. Well, concrete houses, concrete block houses that
No
fall
foundation,
apart.
No,
Yeah,
nothing to
right, exactly.
stabilize them.
And I'm still recording. Okay.
All right, this is lab, I believe, number 3, 4, 5. Lab 5, right? What's an igneous rock? Say again? Yes, a rock that was molten, and when it hardened, it became an igneous rock. As opposed to the other two kinds? Sedimentary, which are made up of either pieces of other rock or chemically dissolved other rock. And then the last is metamorphic. Now, granite is what kind of rock? Igneous, sedimentary, or metamorphic? Nope. Igneous rock. Okay? Give me a few characteristics of igneous rock. Of granite, particularly. Granite. Coarse grain, which means what? Cool deep within the earth. Okay? So even though it's on the surface now, much of this granite, it originally was underneath, and it cooled from very hot magma, slowly making coarse grains. Very good. What else about granite? Anything? Crystals are bigger, that makes it coarse grain. Perfect. Any other things about granite? How about its color? Light colored, which means what? Less iron content. Now the one we're going to be doing today is a bit heavy on iron. You can see a lot of black on this, so the density is going to be a little bit heavier, denser than most granite, okay? Because this has more iron than most does. And the other thing, you don't see very much white in it, meaning it's low on the quartzy type rock. It has a lot of plagioclase, orthoclase, those kinds of things, not as much quartz. Quartz being the lighter. Okay, so this will be a little on the heavy side. Okay, another rock, igneous rock. Oh, where is granite found typically? Second? in the ground. Okay, not flying in the air. Hopefully not. Okay, good. Where is granite typically found? I would say all over the United States. Why? It comprises granite is the primary rock where? In the which crust? Continental crust. So anywhere in any continent, okay, granite is going to be your predominant rock, so to speak. There'll be plenty of others, but that's going to be predominant. What's another kind of igneous rock that's also found in a crust, but not so much in the continental crust? Second, what other crust do we have? The oceanic crust. What's the predominant? Basalt. And we think these are basalt pieces here. So today we're going to be comparing the density of granite to the density of basalt. And we're going to throw in this one. We don't know what this is. Okay? And this is just going to be for fun. But you can put it down, and that may save you from recording be able to get by with 12 if you like. Because we're going to do one other rock, an unknown. We're going to look at what its density is. Okay. Now, what we've got here is a scale. That's the first thing we're going to be using. It says here a balance. We have an overflow can. That's what this is. It's kind of fragile. It's chipped a few times, but I think it'll do well for us. We have a ring stand and a ring, and this container is in the ring. Beaker. This is a beaker. These two are beakers, plastic beakers. And we have a granite specimen and a basalt specimen. So we're coming fairly close to doing what they expect us to do in today's lab. All right. So let's first use the balance to find the mass of the basalt rock. Someone wants to come do that for me. Need a volunteer. Anybody will do. I'll be here till 6, so you can take as much time as you need. Okay. Here are your basalt. First, zero the scale. Be sure you zero the scale and make sure it is on 0. Okay? But then 4 pieces of basalt. All 4 pieces on the scale. Oh,
I'm not sure I'm recording. Yes, I'm recording. Get this close enough so it can hear.
what's the mass of that basalt? Well,
63 grams.
okay. That's 60, 100 what? 53 or 60?
63.
Yes, you say 163 grams. Is that what you said?
Yes.
163 grams was the mass of the basalt. Turn to the very last page, okay, and you see basalt mass. First block there, first column for second row, second column, first row, or second column, row, or whatever. Basalt, the gram, 163 is what you said?
Yes.
That's the mass. 163, right? Okay. All right. Now, we don't have the nylon string. We're not going to do that. Test your tying abilities. Blah, blah, blah. Okay. Now, what we've got to do next is fill this beaker with water. Someone wants to come up and do that. I'm going to try to get out of the way of doing that because I found through experience I have to hold this down. Otherwise, we have some splash action. So I would take the bigger one first. That doesn't matter. Okay. Yeah. Now, why are we doing this? What? Fill it up. All right. I don't know if y'all could hear what he was saying. Is okay. Fill it up. I'll wait. It's not full, is it? Don't hold it together. Is it full yet? Is it full yet? Ah, there it's full. Okay, so we'll take this over to the sink. The sink. Okay, did you hear what he was saying? Especially that irregular piece, that irregular piece. How do you find the volume of that? Very difficult. But if you displace water and then measure its volume, you'll know the volume of the rock. So, I'll need 4 people to drop the basalt in. Now, when I say drop, gently lower the basalt into the water. Pick one of those pieces of basalt. Don't drop. Okay, now, hold by a corner. Okay, and lower it very slowly into the water, but don't get your fingers in. Let go right before your fingers get wet. Okay, displace a little bit of water. Okay, do yours. Need 2 more people. Lower, lower, lower until just before your fingers touch and you release it. Okay, a little bit more. 2 more people. I'm here till 6. Y'all can stay as late as you like. Okay. Slowly, before your fingers get wet. All right. Good. 1 more. Good. Slowly. Okay. Now, oh, I made a mess. All right. If someone will come, actually, someone will come and pour this water into here. Anybody? Okay. Into there. Get it all. Okay. Now, gently, slowly pour that into this graduated cylinder there.
This.
Yeah. That graduated cylinder. Okay. Read the number of milliliters.
50, that's about 60. Let's see.
Each one of those little lines is 2 no. 66? 56. 56 milliliters. That's the salt volume. Now, a milliliter is the same as a cubic centimeter. Okay? So, if we divide the mass in grams by the volume in cubic centimeters, we will have a density. So, if someone has a calculator, divide your...
66?
What did you say?
56,
56 milliliters, which is the same as cubic centimeters.
Um, 2.91.
2.91, did someone else do it too? Chester's checking his math. Okay, 2.91 grams per cubic centimeter. That's the units. A good density measurement. Okay? Now someone else will come over and put the piece of granite on the scale. Anybody? I'm here till 4. Okay? So 0 first, make sure you 0. 0 to scale, make sure it's still 0. Is it? Yeah. Okay. What's your mass? 450 on the nose? Okay, 450 grams. Okay, anyone want to make a guess right now? Is that going to be denser or less dense than the salt?
Denser.
Oh, okay. Let's see. Can someone come very slowly, carefully, gently lower that into the container here?
Will you have to take the
Not
other?
necessarily. If there's enough water in there, I think there is, that you can cover. And I think Chris just showed up. Here's his lab. Chris, here's the lab. I can't move because I'm holding this in place. I'm not that good. Okay. All right. Someone want to come do the density? Drop lower the granite into the water. Anybody? I'm here till 6. Okay. All right, it all went in. Okay? And we caught all the water. Okay? Someone else want to come over? Okay? And pour this water into this container. Someone who hasn't done. I'm here till 6. Okay. Okay, pour this water into here. Slowly, slowly and carefully. Slow down. Okay. You don't want to overfill because, you past your, look at that. He is
Yeah,
wet.
right.
Okay. You have to get one of those others, probably the bigger one. And how much water you got? Will it fit in the little one? No, I don't think it will. It's good and good. Okay, get it on. Okay. Read those two. See what you got. Both of them measured in milliliters. 172. Is that what you said?
Yeah, 172.
Okay. Plus 249. 172 plus 249. 172 plus 249. Huh? 421, is that what you said? Okay. Now take that and divide your mass by your volume. 1.06. Really? Oh, that was less dense, wasn't it?
What was the
Huh?
number?
Why is it doing that?
Because granite is less dense than. Look at that basalt.
What is the number? I didn't hear.
What were the numbers again?
Yeah, 1.06.
That seems a bit on the low side. Are you sure you did the adding of the volumes right? Someone do that?
Yeah, I got
Is that right? Okay. And then dividing right? Okay, that's pretty low. Okay. All right. Now, I'm going to have to take this one out because we can't do the other one. And, okay. If someone could take one of those and pour in here so it flows. Okay. Okay. Now, so I'm going to take that unknown rock and put it on the scale. Anybody? Tired of holding this? No, you've already done. Someone who has it done. All right, good man. 0 to scale. 0. Okay. Well, that's overwhelmed, isn't it? We can't do it, can we? Let me see. Okay, take it off and let me see it. Who would have thought? Okay, let me see the scale come on. Okay, yeah, we can do it. Yeah, let's keep doing it. Okay. You're just going to have to add 500 to whatever you read. Okay, do it again. Did it bottom out? Not quite. Okay, I think we can count this. Second? 650 grams. Right just underneath the bottom. 650 grams. Someone else want to go lower it into the water. All right. Very slowly and carefully.
So are we just calling this unknown
Lower
rock?
that into the water. Good deal. Oh, we splashed a little. Okay. Someone else want to take this and let's see. Pour it into here, but don't. Oh, wait. Probably needed to be a little more careful on that one because we did have some splashing. But someone pour that into there. Someone who hasn't done something. All right, good man. Right here, into that. Work slowly and carefully. All right. What's your the volume? Again. 205 is the volume. Cubic centimeters. Now do your density. This is going to be pretty amazing, I think.
17.
3 point what?
17.
3.17. That was considerably denser than the basalt and much denser than the granite. So I'm going to try to get up from here if I can.
Oh, we're here to see.
Maybe let it stand by itself. Okay. What can we conclude by that? Maybe not too much, but this is denser than basalt. So since basalt is a very high concentration of iron silicate, my guess is this is not an iron silicate. This is more like pure iron. Now, if you remember from the last lab, what were some of the densest materials you had? Those were some of the iron ore type materials. And if this is indeed close to iron ore, which I think it is, then this could be like an iron meteorite. We don't know that, but that would be a pretty good guess. Okay? Certainly much denser than our granite, much denser than the granite, and quite a bit denser than the basalt, which is a heavy iron silicate. So this is probably more like an iron ore, which would fit with what an iron meteorite would be. Okay. That's the first part of the lab. Okay? Somewhere here, everything is such a mess here. Oh, I'm in the wrong spot. Okay. Here we go. All right, that finished the actual wet lab, okay, literally. Let's now turn to our results. In what ways, this is on page 336, in what ways do igneous rocks have different properties? What ways do igneous rock have different properties? What are some of the different properties?
Color.
Second, I heard some things, huh? What'd you say? Color. Color was one. Texture was one. Second. Hardness. Okay. Others? Mineral content. Excellent. Others? Density, what we were calculating today. They definitely have different densities. Okay? And there's probably some of the others too. Now, number 2. Explain the theoretical process or processes responsible for producing different properties of igneous rock. Take one of those properties. What's the first one mentioned? Color. What would be a theoretical process or processes for responsible for producing different colors in rock? Yes, the amount of iron. Okay? Now, if you think back, remember that thing called Bowen's something another scale? Okay? The higher iron content comes out of solution at higher temperatures. And then as it cools, then lower iron content, then lower. So you see the temperature of cooling would also be another theoretical process responsible. That's responsible for how much iron is in there, which in turn is responsible for the color. So
where it is on the Bowen's temperature scale. That would be another. What was one of the other properties? Second? I can't hear.
Texture.
Texture. Okay, what determines the texture?
The temperature. It cools.
The what?
The temperature it cools at.
Okay, close but not quite.
How quickly it cools.
Okay, the cooling rate. Texture is determined by the cooling rate. And how does that work?
It's above the surface or below the surface.
Okay, and what difference in cooling rates does that cause? Below the surface we cool
I read the
more, no, below the surface more slowly, above the surface faster. And how does that affect texture?
When it's above the surface, it's smooth. When it's below, it's very coarse.
Okay. Yeah, when it's below the surface, larger crystal sizes, coarser texture. Near the surface or at the surface, more rapid cooling rate, smaller crystals, finer texture. Right? Okay. Was that much? Oh, no. Was another property. The density. Let's talk about density then. What's that related to? Primarily. Iron content again, so that is going back to the same thing as the color. Okay? The higher the iron content, meaning the higher the temperature at which it came out of solution, out of the magma, and hardened from the magma, the greater the iron content. Later, at the lower temperatures, more silicon. Y'all are good at this. Number 3, according to the experimental evidence in this investigation, propose an explanation for the observation that the bulk of the Earth's continents are granite and the basalt is mostly found in the Earth's interior or at the bottom of the ocean. Why would that be the case? Second?
The different densities.
Okay, different densities. The basalt would settle out lower and the granite settle out higher. You're absolutely right. Even though the basalt seemed to be finer grained, which cooled more rapidly, but that's because they were usually on the bottom of the ocean when they cooled, and so they cooled very rapidly. All right. Now, question number 4 is completely up to you. If it's not answered, you lose a point, but if you answer it adequately, it's otherwise. We did 9 on the back rather than 6, so we have done 12 questions. No, 9 and 13 questions, right? 4, 9, and 13. Good. Okay. And that leaves 12 questions to go. So the other 12 questions come from those at the end of Chapter 18. For further thought and questions for thought and for further analysis. 16 questions for thought. Y'all like that? Okay, good. 4 for further analysis. Of those 20 questions, answer at least 12 of them. Any that you do beyond that, good. Now, that will conclude the lab. If you finish those before the 2 hours are over with, you can turn them in. If you don't, you can stop and take your test. The more you answer, I bet you the better you'll do on your test. I can't guarantee that, but my guess would be pretty close to that. Okay, are there any questions? Okay, I'll go on and shut down the recording and get it uploading.